Mm.
If you could sing it with me, I'd let you stay. But
I can't leak the strats.
I don't think you can hit the notes either. Sorry about it.
Bro, huh? I'll hit you.
Not if I
One needs to mute.
Oh, hey!
Get rolled. Stop. You're gonna mess up my headband. Stop. You're not talking.
Brett, your mic is still on.
You did the Donkey Kong move from Smash Bros. Stop.
Hello, everyone. Today is a review for exam 2, which will cover the chapters that we discussed already. I guess we start out with the capacitance, chapter 25, 26, the introduction to resistivity or resistance, and then also circuits in terms of understanding how to diagnose a circuit, Kirchhoff's laws, RC circuits, and we got halfway through chapter 28, my introduction to magnetic fields. So like last time, same format, I'll just start going through examples, some candidates that could be on the exam. So let's get started. So let's look at this first case. We have a parallel plate capacitor, has plates with area of 0.4 meters square. The plate separation is 0.2 millimeters. The capacitor is connected across a 9-volt source. The question is, what is the magnitude of the electric field between the plates? And then we want to determine the capacitance. So what we know, there's a relationship between the potential and the electric field through a path integral. You guys remember? You are seeing a path integral, I assume. Hello?
Yes, we see it.
Okay, just want to confirm. All right. I recall the electric field near the surface of a charged plane is nearly uniform. So that being the case, electric field is constant everywhere in this volume between the plates, and D is the separation between the plates, D being 0.2 millimeters. So what we want to do now is solve for E in terms of the voltage and the separation. And so now we have this relationship, and pretty much we have all the known variables here. I mean, there's for voltage is 9 volts, and for the separation is 0.2 millimeters. And we basically plug these values into the relationship. And we arrive at a fairly large electric field. That being because the separation is tiny, 0.2 millimeters, but it's 45 times 10 to the third volts per meter. So any questions about that part before we move on to part B? Okie dokie. We know the relationship between the plate geometry, in terms of separation, and the capacitance. So we have the geometry factor, which is the area on the plate divided by the separation, times epsilon naught, gives us the capacitance for this particular. Hello? Was there a question?
It was just echo.
Oh, okay. I mean, I'm talking too loud. All right. So we have the area. I mean, that's given to us in the problem. Separation is given to us. Epsilon naught. I mean, if this was on the exam, epsilon naught would be given to you. And that's 8.8, 8.85 times 10 to the minus 12 coulombs voltmeters. And evaluating this on a calculator, we get 17.7 nanofarads. Okay. Now, if we wanted to know, if there was another question that says, well, what is the charge on this capacitor? How would we determine that?
Wouldn't we just use the definition, which is Q over delta V?
Yeah, I mean, basically CV equals Q, basically. But yeah, the definition is, you say, is Q over V equals the capacitance. So that's how you would do this. All right. Pretty straightforward problem, I think. Famous last words. All right, let's move on to the next problem. Okay, so we have this capacitor, I'm calling C1. I give it a value of 30 microfarads. And it's charged to 80 volts. And then it's disconnected from the power supply and then connected across uncharged capacitor of unknown capacitance C2. And if the final potential difference across the 30 microfarad capacitor is 20 volts, what would be C2 in this case? So let's draw a little diagram first showing us charging the capacitor, C1, which we already know the value of to be 30 microfarads. And once it's completely charged, then we disconnect the power supply and then attach C1 to C2 in the following manner. Okay, well, the voltage drop from 80 to 20 volts when connected to C2. The charge, initially on C1 is now shared with C2. So there's obviously is less charge across C1. A couple other points here to make. Charge is conserved, so the amount of charge initially on C1 at 80 volts must equal to the total charge on both capacitors. There's this other point too, the equivalence for the parallel capacitors. It's just the sum of the two in this case when they're parallel. Unlike that for the resistance. And of course, as we know, the parallel capacitors, anything that's in parallel of each other, be it a resistor or inductor, which we'll learn about hopefully before the end of this course, they will have the same voltage across each component that's in parallel with each other. That being the case, we can write this in the following way. The voltage across, the equivalent capacitance is equal to C1 times V plus C2 times V, being that the voltage across C1 and C2 are the same. And just recall the relationship that CV is equal to Q. All right, and this relationship we were taught earlier that the initial charge on C1 must equal to the total charge on both C1 and C2. So what I have here related to that is C1 times 80 volts, this is when it was isolated from C2, must equal to equivalent capacitance, C1 plus C2 times 20 volts. So basically what happened, the amount of charge that was deposited on C1, it's just now, part of that is on C2 now. The charge has no place to go. Okay. And so what I'm doing is to substitute in for the equivalent capacitance, C1 plus C2. So now we have this relationship. And now we can solve for C2 in terms of C1, which we know the value for. And so basically it's a little bit of algebra here. Combining terms, 80 minus 20 divided by 20 we know is 3. Becomes 60 divided by 20 is 3. And so we just multiply 3 times 30 microfarads. And that gives us 30 microfarads. Oh, wait, that should be 90. Hang on just 1 minute. Mistake here. That should be 90, right? Or I get scolded by someone. Okay. Much better. Any questions about this?
Aren't those capacitors, you said those are in parallel, not in series?
Those are in parallel. Yeah, I mean, that's the way we started out. We have a voltage across C1. And then, after we disconnected it from the 80 volt power supply, we moved it over to the other side and attached it to C2. At that point, the voltage across C1 and C2 are the same by definition. So, being that a conductor, everywhere on a conductor has the same potential, right? And you would assume these lines have they're perfect conductors. I think I know what you're saying. I mean, if we had like a current that's going through a loop like this, you could argue in that way that it's in series.
Yeah, that's what I was thinking.
Yeah, but in this case, the way we attached it, I mean, I could have, in fact, put a couple of stems, like one on the top and one on the bottom, to resolve that. But at the time that we attached C2 to C1, it's C2 it has no voltage across it. So for a short time, there is a current, of course, that's flowing from one capacitor to the other, and in fact, it's really not infinite, being that the wires here, it has some conductance associated with it. I mean, there's a RC involved, but yeah, I mean, I guess you could try to treat it the other way, but it's not as straightforward. So in this case, I would treat it, in fact, if we want an equivalent voltage, both of them having the same voltage, what we know, yeah, I don't know how to really approach this from the series point of view.
Couldn't you just solve for the equivalent capacitance and then do that times the
Oh yeah, I mean, you
final
could
potential
do
difference?
that. I mean, yeah, I mean, that is certainly something. There's multiple ways of solving the problem. Yeah, I mean, we could, but the fact of the matter is that we don't know what C2 is. That's the whole point of going through this route. I mean, another way to look at this, you can determine how much charge was lost on C1. You can calculate the amount of charge on C1, when it's fully charged to 80 volts. You can determine, whatever that is. Remember CV, so it's 30 microfarads times 80. So that's 240 microcoulombs, right? Well, no more. It's actually 2.4 millicoulombs. And then once, the voltage drops on C1, you know how much charge was lost, how much charge was given up to C2. So that's another way of solving the problem without even going through the equivalence. Just calculating the amount of charge that was transferred from C1 to C2 would bypass the need for doing the equivalence. Is that understood? Does that make sense?
Yes.
Yeah.
Yeah, I think so. Thanks.
You think so? All right. I guess that's a better no. All right. Let's move on to the next problem then. All right. Let's see. Okay, we want to determine how much current will flow through a 40-meter length of cylindrical metal wire. It has a diameter of 2 millimeters. Now be a little careful like this on the exam if this is given radius versus diameter. I mean, it's just a small issue in terms of points, but just remember you want to, if you're doing, if you want to calculate the area, which you will have to in this case, you want to convert this to radius. And so, okay, it's connected. This wire is connected to a power source of 16 volts. And the resistivity of this metal is given as 1.68 times 10 to the minus 8 ohm meters. And okay, so this is the information given to us. Now we want to determine the current, and so obviously the natural choice is Ohm's law for calculating the current, but we must first determine the resistance of this length of wire. Okay, so we have Ohm's law, relationship between the current, voltage, and resistance. And the geometry of the wire is provided, so we can use this relationship between resistance and resistivity. Where rho is the resistivity of this material, whatever that might be. It could be maybe copper based on the number. All right, so the length is given to us. We have to calculate the area. Okay, so, all right, let's move forward from this. So I decided to put everything symbolically to the very end. So we have Ohm's law. I now want to substitute the resistance into Ohm's law equation, and so that's why we get the second term as it is, where now area is in the numerator and resistivity and the length is in the denominator. And now put in values for this. So in the numerator here, this is the area for a circle. Remember, this is a cylindrical metal wire, being it, but that basically means the cross section of this wire is a circular. Notice I divided by 2 before squaring it. And resistivity, the length, and the voltage. Putting all this together, you get pretty large current, 74.8 amps. So I suspect the this wire would heat up a bit. Any questions?
Just generally, would you say that, I mean, because we've done these 3 so quickly, there's going to be more than 4 problems on this exam?
There'll be 4 problems, just like the last one.
Oh, only 4. Okay, cool. Thanks.
Yep. Mm-hmm. All right, moving on. Okay, so we have a battery, and we're placing a 74 ohm resistor across the terminals of this battery. And a quarter amp passes through this resistor. So we want to determine the internal resistance of the battery based on this. oh, wait a minute, I forgot to put, this is supposed to be at 12, hang on, just a minute. Oh, good grief. Give me one moment, I left out something. Something kind of important, actually. The voltage, like the EMF of the battery, sorry. There you are. So this is the EMF of the battery. And we measure 0.25 amps through the resistor. And so the question is, what is the internal resistance of the battery? And then after we determine that, then we want to determine the ratio of power dissipated by the internal resistance, a resistor, to that of the external resistor. All right, so let's put down the circuit diagram. That's what we have. Again, what's in this dashed line is within the battery, it's hidden to us. And it's, you have the EMF, and the EMF is 12 volts. Little r is the internal resistance that's unknown to us. But big R is known to us. And also the current, we measure the current. So what we'll do is just use the loop rule. So we have the EMF, which we know is 12. Current, since it's a single loop, has no place to go. So the current's the same everywhere in this circuit. So going from C to D, we have a drop in potential. So that's a minus I little r. And as the current leaves or exits the terminal, positive side of the terminal, it goes through big R. And so the potential drop across big R is minus I times big R. And sum of that must equal 0. So what we want to do now is we want to solve for the internal resistance little r. And we can isolate it now. All the other variables are known. So the internal resistance is equal to the EMF divided by the current, all that ratio minus the external resistor, which is, we know, 47. So just put in the values. We have 12 volts divided by the current, quarter amp, minus 47 ohms. And this turns out to be 1 ohm exactly.
I have a question.
Sure.
Why isn't it the resistor times the current? Like, where did the I go from the original loop rule?
From here, you mean?
Yeah, right there.
From here to here?
Yeah.
Okay, well, you just divide everywhere by I, the current.
Oh, okay.
What's that?
I said, okay. I see where, and then it cancels out.
Yeah, okay. I think that's one of the shortest answers I've ever given. All right, I'm on a roll. So now what we want to do is determine the power dissipated by the internal resistor. Remember, we want to find a ratio of the power dissipated by the internal resistor to that of the external resistor. So let's first start by the internal. And we know it's just I squared divided by little r is that dissipated by the internal. And by the external, the same form, which is it's I squared times big R. That's the external resistor. So take the ratio of these two. You can see the currents cancel out. So this is basically the ratio of the resistors, which is the ratio of the power dissipated. Any questions? Okay, let's go on to the next one. All right,
Can
so
you go
this
back
is,
to the last slide real quick?
sorry?
Can you go back to the last slide real quick? I was just writing something down.
Oh,
Thank you.
sure, yep.
I'm good now. I appreciate it.
Sure, no problem. Okay. So we have, in this case, a capacitor. Let's show the circuit here. So the switch initially is open, and this capacitor, kind of like in a previous problem, is charged to 80 volts. Okay. And then what we'll do is we'll close the switch, and we say this happens at t equals 0. We have to give it some initial condition. And how long after closing the switch will the current in the resistor be 7 microamps? Remember, when we first close it, that's when the current will be at its maximum. Because that's at the point in which there's a maximum voltage across the capacitor. And you can think of these are in parallel if you like, in a given instance. And so the voltage across the capacitor must equal that across the resistor. And then as the capacitor discharges, its voltage goes down, and consequently the voltage across the resistor goes down, and then the current goes down. So we want to know when it reaches 70 microamps. As I just stated, capacitor is charged to 80 volts, and when the switch is closed, the capacitor discharges through the resistor. So what we need to know is the time dependence for the current while discharging. I think we know this. In fact, I think this is an equation in your reference sheet or something close. Alrighty, so this is the time dependence for current, and of course this is for the discharging case, not the charging case, but actually I think it's very similar for the current, identical. Very different for the charge, so for the charge across the capacitor. All right. So we must solve for the time in this case. Have to do a little bit of algebra to do so. So the first thing I want to do is multiply both sides times R and divide both sides by V naught. And V naught, of course, is 80 volts, if we start out with that. Right, so now we have this relationship. We have this exponential we need to take care of. The best way to get rid of the exponential is a log. So taking a natural log on both sides will give us this. Remember, log of the exponential basically nullifies the exponential. We just bring down whatever is in the exponent of this e. So that's basically what has happened here in this operation. You still have the log of these terms, these three terms here. Okay, so now what I want to do is multiply both sides times RC. And the minus sign, that must carry through. Okay, next step is just to evaluate this. We have all these numbers available to us. Okay, this big M means mega, so that's like 10 to the 6. So this is the RC part of the equation, values for that. This is the current. We're evaluating the current. We want to know what the time is when this amount of current that's passing through the 28 or 2.8 mega ohm resistor reaches 70 microamps. And resistor again, and the voltage. Evaluating all this, it's 86.6 seconds for this given case. Any questions? Okay. Number 6. All right. Double loop. This is not a bad problem, actually. Things tend to cancel out. So in this circuit diagram below, first what we want to do is just find the magnitude and direction of the current in the 5 ohm resistor, which is here, and then the power dissipated in that resistor. All right, so we have 2 power supplies, 10 volts, 15 volts, and then we have these 2 other resistors, 15 ohms and 30 ohms. So go through a method of marking the direction of the currents, our choice of the currents. And that's what we will do here. You know, once we do mark the currents, the direction that we pick, I mean, they're not necessarily in the correct direction, but it doesn't matter. We just need to give a direction and do the calculation. And it's a positive sign for the current, then you pick the right direction. If it's negative, then you just do a 180 on the current. Okay. So we'll look at the junction rule at B. I1 plus I3 equals I2. For loop 1, let's start at the case here for the 10 volts of the power supply. So we have a plus 10 volts going across the 5 ohm resistor. Got a plus to a minus as a result of the current going in that direction. So we have a minus I1 5 ohms. And going through that middle branch down from B to E, we have I sub 2 going across 15 ohms. And then there's nothing else to add to our voltage loop 1, so that's set to 0. Do the same for the other side. All right, so start here at the bottom. We have really I3 here at the top. Of course, you know I3 must be at the bottom since I3 has no other place to go. There's not a branch. So we have I3 times 30 ohms plus 15 volts across that power supply. And nothing here. And then down again through this middle branch, which is I2 times 15 ohms. Okay, so now we have our 3 equations. So what we'll do first now is substitute I sub 2, the current junction equation, into the loop 1 equation. This equation here. We want to get rid of I sub 2. Remember, it's I sub 1 that we're really interested in because that's the current that goes through the 5 ohm resistor. Okay, so this is what we'll do. We eliminated I sub 2. We're going to combine terms. Combine this term, I sub 1 times 15 ohms to the 5 ohms. So we'll then have minus I120. And we just moved over I sub 3 over to the right-hand side of the equal sign. And what we'll do now is we want to solve for I sub 3. And doing so, we have this relationship. Okay. Same thing for loop 2. We want to get rid of, we'll eliminate I sub 2. We'll do the same thing. Again, this is this equation here. We've already made the substitution. Okay, now same thing. We want to combine terms. There's 2 I sub 3 terms. I moved over I sub 3 over to the right-hand side. So I sub 3 here, you got a 15, you have a 30, 15 plus 30 is 45. We'll move over to the right-hand side. And again, what I want to do is isolate I sub 3. Okay, so we have two equations for I sub 3. All right, so we just equate these together, right? And doing so, we have this relationship. We have a single equation for I sub 1. We can solve for I sub 1. It turns out to be 1/3 of an amp. Okay, we're not done yet. All we have done is just determine the current through the 5 ohm resistor. Now we want to determine the power dissipated in the resistor. This is actually pretty straightforward because we know the current, we know the resistance, I squared R is what we would use. And basically, what we'll do is just square the 1/3 here, you get 1/9. And so it becomes 5/9 watts in this case. Not so bad. Any questions? Did I stun people? Is anybody there?
Could you go over how you got the 3 equations again really quick?
Oh, at the top here.
Yeah.
Okay. Well, the junction rule, that's just based on charge conservation. So the amount of current that goes into the junction must equal to the amount leaving the junction. Right. So we have at least the way we have this designated initially. You know, I1 is going into junction B, I3 is going into junction B, and I3 is departing. So you're okay with that?
Yeah, that makes sense.
And for the next one, the loop actually could go in either direction. I mean, once we establish the direction of the current, and, I like to put the plus or minuses here, just, I don't know, it's kind of redundant, but at least this reminds you, which direction is the potential drop based on our choice of current. But I chose to go in this direction, clockwise direction, starting out with the power supply minus the plus. The power supply gives us a positive plus 10 volt potential. And then the current I1 through the 5 ohm resistor, that's a potential drop. So that's current 1 times 5 ohms. And then going down through the center branch, current is I2 times the resistance in that branch is 15 ohms. And then to make the complete loop, we go back to D and then we're done. I mean, then it's there's no added components needed from there. So we set that equal to 0. So is that okay?
Yeah, I think I get the other one too.
Oh, okay. All right, good.
Yeah, thank you.
Sure. All right, so let's go to this next one.
I have a question actually.
Sure.
So we're using, oh wait, never mind. We're using I1 for the power dissipated, right?
Using I1, I'm sorry, I didn't catch that. My hearing's not great.
We're using, oh, okay. I mixed up which current we were using because we're using I1 to find the power dissipated, right?
Yeah, I mean, yeah, because that's the current that's flowing through that particular resistor. I mean, we could have picked, for example, the middle resistor, and then we would use I2, but we would have to calculate I2 first, or the voltage. Yeah. But yeah.
Right. Okay.
Yeah.
I think I got it.
Yeah.
Sorry.
Okay. Is any other questions? Okay, we'll do a magnetic field problem next. Okay, so in this diagram, I have a particle of charge -7 times 10 to the -6 coulombs. Note the minus sign. And it has a mass of 3.1 times 10 to the -12 kilograms. It has a velocity of 9.4 times 10 to the 3 meters per second as it enters a region of a uniform magnetic field. Of course, you know that will be constant. Magnetic fields, at least static magnetic fields, cannot do work on moving charges. Particle is observed to travel in a semicircle path, as shown in this diagram. It has a radius of 50 centimeters. So what we want to do is calculate the magnitude and the direction of the magnetic field in this region. It's a little opposite of what we have done in the past. We usually are given a magnetic field, and we determine some of these other parameters, but this is a little different in this way because that's unknown to us. We just know the geometry of the trajectory. Okay. So we have this relationship for gyro radius is equal to mass times the velocity of the particle divided by the charge of the particle and divided by the magnitude of the magnetic field. Okay. Another thing too, which probably should be specified in this problem, is that the trajectory remains in a plane. It does not have a helical type path. So if such a problem is on the exam, then it should be specified. All right, so what we want to do next, though, is to determine the magnetic field in terms of these parameters. So these parameters are given to us in the problem. We have the mass, we have the velocity, we have the charge, we have the radius, the gyro radius. So we now can just isolate the magnetic field. Pretty much we have everything we need at this stage. So the mass is given to us. Also the speed or the velocity and the charge. Oh, shoots. This should be, hang on a minute. This is actually a typo. So I don't think it's complaining a lot. And this is just a typo. I don't think it, I may be wrong with it. Okay. Double check the math on this, but I think this is right. So, sorry. So now that's correct. It's a half a meter. And I got a number 8.3 times 10 to the -2 Tesla. You guys are invited to convince yourself these numbers are right.
I have 10 to the -3rd, I think.
Yeah, okay, so I did in fact, the typo. Does anybody else see the same thing?
Yeah, I had
Yeah.
10 in the minus.
Okay, so the typo was, actually one or two things I could have changed what's in the text. But let's just do this. All right. So the typo was carried through. All right. Now this is a little, in terms of determining, the direction of the magnetic field is not, right-hand rule, as you remember, typically what we do is we point our fingers in the direction of the velocity of the particle, and then we bend our fingers in the direction of the magnetic field, and our thumb points then in the direction of the Lorentz force. But we don't have, we don't know what the magnetic field is, the direction. We see though, the particle's trajectory is deflected to the right though. If it wasn't for the magnetic field, I mean, if it's just in a vacuum, there's no other forces acting on it, the particle would just continue to move in the upward direction, right? So, yeah, this is, as I just pointed out, you know, you right hand rule, you point fingers in a direction of the velocity and bend the fingers toward the magnetic field, and then your thumb points in the direction of the force. But the magnetic field direction is unknown. The forward direction is implied, though, that from the deflection of the trajectory, that it's in the right, it's toward the right direction. So in this case, you point your fingers toward the initial velocity vector, and then your thumb points to the right. That's just the force direction, and then your fingers will tell you then the direction of the magnetic field, which is, based on what I just said, is out of the screen. But since the particle is negatively charged, we reverse, we do a 180, and so the field, in fact, is going into the screen. A little bit tricky here.
So because the charge is negative, it's like 180.
Exactly. So as opposed, I mean, you know, I guess we could use your left. I mean, I don't know. I don't want to confuse folks here, but you know, if this is a negative charged particle, one idea is to use your left hand. So if you were to point your fingers in a direction on your left hand, in a direction to the velocity of the particle, then point your thumb in a direction of the deflection, which we know is the direction of the force, just as it's entering into this region, right? You know, right at the boundary, and then wrap your fingers, your left hand fingers, and it would go into the page. In that case, but you know, if you want to do the right hand rule, you would just have to do a 180 because it's under, you know, it's under the assumption that you're doing this for a positive charge particle.
Could you possibly go over the right-hand rule for that again?
I think that Dinesh uses a slightly different method of doing the right-hand rule.
There's many different methods, and do what's best for you. That's all I can say. I mean, it's my choice. I guess is part of the, I don't know if there's actually a name for the different types, but my choice is like what I just described. So if you have, your velocity crossed into the magnetic field, and the resultant is the force, or proportional to the force, then you point your fingers in the direction of the velocity. And then try to rotate your wrists without hopefully breaking anything, such that you can wrap or bend your fingers in the direction of the magnetic field that is given to you. And once you do that, your thumb will point in the direction of the force. V cross B is proportional to the force.
So for this case, the initial velocity, like even though you have that little arrow in the diagram, it's actually like upward, right?
It is. I mean, in fact, this works anywhere on this trajectory, actually, if you wanted to do that. But you got to keep in mind, like it's like at the top of the trajectory, at the point where it's maximally extent into the magnetic field region. So now the velocity is toward the right as opposed to upward. But then the force is downward. It's deflecting the particle in the downward direction. That's the direction of the force. So yeah, I mean, he actually can pick any point on this trajectory, and he should give you the same result for the magnetic field or the force than what's given to you. The fact that the magnetic field or the force is always perpendicular to the motion, like that of centripetal force. Okay, I wanted to go through another magnetic field problem. All right, so we have an electron that follows another negative particle. And it follows a circular path, an uniform magnetic field. And this is 3 × 10⁻⁴ Tesla. Actually, it's also 3 × 10. This is actually the same as Gauss. I think that's like 3 Gauss, but just keep it in Tesla because that's SI units. And the question is, what is the period of this motion? Okay, this is what's given to us. We have the mass. Well, I would in fact give you the mass of the electron if that was given. I mean, that was stated here, as well as the charge, and the field is given in the problem as it is. Remember the angular frequency, which I think is in the reference sheet, is given as the charge times the magnetic field divided by the mass. But it's the period what's been asked. Remember, the period is equal to 1 over the frequency. And the frequency is equal to the angular frequency divided by 2 pi. Okay, so the frequency looks like the number of cycles, full cycles in this case, but here, for angular frequency, it's the number of radians per second, which is, there's 2 pi radians in a circle. All righty. Hope you guys remember this. All right, so we can now substitute for omega, which is 2 pi times the mass divided by the charge, the magnitude of the magnetic field. And from that, we have all the values. I mean, we have all the parameters are known to calculate the period. Okay, and evaluating these values on your trusty calculator, we get 0.2 times 10 to the minus 6 seconds. So it's 0.2 microseconds. Well, as usual, I'm fashionably going over the time limit. We're right at 1 minute over, so I'm going to have to stop here. Actually, I only had one more, but it was just sort of an optional problem. It's an event that I went through these problems faster than expected.
Post these on Canvas, right?
Well, yeah, Canvas as well as on the calendar.
Sorry, can you say that again real quickly?
Oh, Canvas, well, it will be posted on Canvas as well as the calendar.
Okay, thank you.
Yeah.
Thank you.